Welcome to homework.
For this question, we're given an expression for the electric field E in free space. We're told it's equal to E naught times sine kx minus omega t in the j hat plus E naught cosine kx minus omega t in the k hat. And for the magnetic field B, it's B naught cosine kx minus omega t j hat minus B naught sine kx minus omega t k hat. So to avoid having to write kx minus omega t, since the sine and cosine terms all contain that, I'm going to do a variable switch. I'm just going to call delta kx minus omega t. So anytime I write delta, that's what that means. So it's just avoiding having to write that over and over again since we're writing a lot here. For part A, it says show that E and B are perpendicular to one another at all times. Okay, so to do that, all we need to do is show that the dot product between the two is equal to 0. If it is indeed equal to 0, then we know that they're perpendicular to one another at all times. So we do E dot B. So when you do the dot product, you can only multiply like components. So the I hat and the j hat components from E and B get multiplied together. So what we have here is E naught times the sine of kx minus omega t, which I said was delta, times B naught times the cosine, B naught, not just B, B naught times the cosine of kx minus omega t, delta, minus E naught times the cosine of delta times B naught times the sine of delta. So essentially, we're taking E sine delta B naught cosine delta and subtracting it from E naught sine delta B naught cosine delta. Since everything's being multiplied, it doesn't matter the order of multiplication. These two terms are equal to one another, so this comes out to equal 0. And since they're equal to 0, we can say they're perpendicular to one another. So we can say, thus, they are perpendicular to one another. We can box that in as a solution for part A. Part B says for the E and B waves in plane that are parallel to the YZ plane, so that the waves move in a direction perpendicular to E and B. So the direction of propagation is perpendicular to E and B. So to do this, we need to show that the cross product, the pointing vector, is perpendicular to E and B. It's going to need a little bit of space, so let's start a new page here. So the pointing vector, S, is defined as 1 over mu naught. Again, the pointing vector is the direction of propagation. It's 1 over mu naught E naught cross B naught. Or excuse me, E cross B. Since we're considering the vectors in this case. Okay, so we can use the matrix table here to more easily do this cross product. So this is equal to, we have 1 over mu naught, since that's just a constant, we'll pull that out front. So the directions we have here are I hat, j hat, and k hat. Okay, well, there is, for both E and B, there's no I hat direction. The j hat direction here is, for E, is E naught times the sine of delta. For j hat, for the B field, magnetic field, it is B naught times the cosine of delta. Let me make sure I got enough room to write the k hat. Let me get rid of this to move that over a little bit. Okay, so the k hat for the electric field is E naught times the cosine of delta. And for the electric field, or for the magnetic field, it's minus B naught times the sine of delta. Okay, so if we carry out this operation here, we find that this is equal to 1 over mu naught still, times, okay, so the first one is minus E naught times B naught and since both of these, so what we're doing here is we're multiplying this together here, those two that I just crossed in red. So this is minus E naught times B naught times the sine squared of delta, since they both have the sine of delta term. And then we're going to subtract from that the cross multiplication in this direction. So this is minus, again, you have E naught times B naught times the cosine squared of delta. And this is in the I hat direction. The reason it's in the I hat direction is because the cross product between J and K give us I hat. Now, if you did the same thing for the J hat and the K hat, they would be multiplied by that I naught, the I naught terms, but the I naught terms are 0. So this would be plus 0 J hat plus 0 K hat. So we just have I hat directionality here. So we can pull the E naught and the B minus E naught and B naught out front. So this is minus 1 over mu naught times E naught times B naught. And then this is going to get multiplied by sine squared delta plus cosine squared delta. But sine squared of a value plus the cosine squared of a value is just 1. So that's equal to 1. So this is minus 1 over mu naught E naught B naught in the I hat direction. So again, the trick that we used here is, so in general, cosine squared of delta plus sine squared of delta is equal to 1. That's just a trigonometric identity. So that's what we use there to simplify that. So we have minus mu naught, 1 over mu naught, E naught, B naught in the I hat direction. But the I hat direction is perpendicular to J hat and K hat. And E and B move in the J hat, K hat direction. So we can say, thus, it is perpendicular. I'm just abbreviating perpendicular to E and B, where E and B are both vectors, so maybe we can indicate them as vectors. So I'll put a little vector symbol above both of those, and we can box that in as the solution for part B. Part C says it would like us to find the magnitude of the electric field and the magnetic field. So to find the magnitude of the electric field, it's just equal to using a Pythagorean theorem. This is equal to the sum of the squares of all the sides that make it up, square rooted. So this is equal to E naught squared times the sine squared of delta plus B naught squared times the cosine squared of delta. Or excuse me, this is E naught because we're considering only the electric field components. So this is E naught. Okay, so it's E naught sine squared delta plus E naught cosine squared delta. Well, E naught's just a constant, so we can pull E naught squared out of it, but E naught squared gets square rooted, so that's just E naught. And inside the square root, we're left with sine squared delta plus cosine squared delta, which again, we already said is equal to 1. So this is just simply equal to E naught. We can box that in as our solution. Now for the magnetic field, B, again, this is equal to the square root of the sum of the squares that make up all the sides. So this is B naught times the B naught squared times the cosine squared of delta plus B naught squared times the sine squared of delta. Again, B naught is just a constant, so B naught squared can be pulled out, but B naught squared is inside the square root. So B naught squared square rooted is just B naught. So we pull a B naught out front, and then inside the square root, we're left with cosine squared delta plus sine squared delta, which again is just equal to 1. The square root of 1 is 1, so this is just equal to B naught. And we can box that in as our solution to the final part of part C. And lastly, we have part D, where for part D, it says to At x equals 0, draw the orientation of E and B in the y-plane at t equals 0. Then qualitatively describe the motion of these vectors in the yz plane as time increases. Okay, so first thing I'm going to do is draw it, and then I'm going to explain that qualitative explanation they ask for. So here we just drew the yz plane, so we'll call this the z direction, and we'll call this the y direction. And in blue, I'm going to draw the electric and magnetic fields. Electric field here is along the z direction, so here's E naught. Magnetic field is along the y direction, so here's B naught. Okay, so in the picture, the x-axis is out of the page. With increasing time, the electric field component in the z direction becomes smaller, and the component of the electric field in the negative y direction becomes smaller. Okay, simultaneously, the magnetic field component in the y direction gets smaller, and in the z direction gets larger. So due to resultant effects, the electric and magnetic field vectors rotate counterclockwise. So that would be the qualitative solution to that question. So maybe we could say that the electric field in the z direction and in the negative y direction becomes smaller. So let's say E field in z and negative y direction becomes smaller. B field in the y direction gets smaller, and in the z direction gets larger. Thus, the electric and magnetic field vectors rotate counterclockwise. That would be our answer to the question.